Next, I want to look at some common bases that we see with logarithms. Now, you can see different kinds of bases as well, but there are a couple that tend to stand out as being used the most frequently. And the first is base 10. So we actually call this the common logarithmic function. So a function with base 10 is called the common log function. And what happens is we actually end up dropping the 10 from the notation. So if there's no number, so if there is no base, then you always assume that the base is equal to 10. And again, it's just because it's used so frequently. It's the same idea when we have a square root. We don't usually write the 2 in for the index like we do with a cube root or fourth root. It's just used very frequently, so we drop it. So if you don't see a base, there's always a base 10 there. So the percentage of adults' height attained by a boy who is X years old can be modeled by the following function. Notice that there's no base here, so this is assumed to be the common log function with base 10. X represents the boy's age, and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at the age of 8? So here we're looking at when x is 8. So we're going to go ahead and plug this into our function. Okay. And I'm just going to start simplifying here. So one thing I do want to note too is when you have a number next to a log, there is a multiplication symbol there. Again, we often don't write multiplication symbols in when two things are touching, but it is implied that that would be multiplication. So you're looking at 29 plus 48.8 times the log of 9. Now, order of operations says that you should multiply before you add. So you're definitely going to need to use your calculator here. So I'm taking out my calculator. And again, if you have a more, not even super, but a slightly more advanced calculator, you should have a log button on it. So if it says just log, that is assumed to always be base 10. So again, most calculators provide functions for base 10 and base e, but not the other ones. So for base 10, you should be able to find that. So what you're going to do is hit log 9. So log and then type in 9, hit enter. And that is that log value. And you want to use all those decimal places. So if you want to write it out, you can. I'm just going to leave it in my calculator and I'm going to multiply that by that 48.8. And now I have 29 plus 46.5670346. I add 29 to it, and I get 75.5670346. When you're dealing with exponentials and logs, I highly, highly recommend you use all the decimals that are given. There are very easy ways to get rounding issues here because the numbers grow in certain areas so quickly that a rounding issue can make a really big difference. So use all your decimals and then round at the very end. So for this one here, let's say we just round to the nearest percent. So we're looking at the nearest whole here, that 5 is going to bump this up to about 76%. So at 8 years old, a boy has attained about 76% of their height already. That's pretty interesting. All right, let's look at another application here. So the magnitude R on the Richter scale of an earthquake of intensity I is given by R equals log I over I sub 0, where I sub 0 is the intensity of a barely felt zero level earthquake. The earthquake that destroyed San Francisco in 1906 was 10 to the 8.3 times as intense as a zero level earthquake. What is the magnitude on the Richter scale? So that scaling for earthquakes is actually another application of the common log. And there's no base here, so you're assuming that it is base 10. So here what we're doing is we're plugging in the following. So the intensity level in this case is 10 to the 8.3 times as intense as a 0-level earthquake. So times, and then a 0-level earthquake is just I sub 0. So times I sub 0. So if I plug this in, I have log. So my intensity is 10 to the 8.3 times I sub 0 over that I sub 0. Those i's are going to cancel out. And then you just have log of 10 to the 8.3. Now you can do this on your calculator. So let me show you that. So I would hit that log button, 10 to the 8.3, and I get 8.3 right out. Now, another way you can do this is you can think back to some of those properties. So remember that this is base 10. So this is your inverse property. When you have log base 10 to 10 to some power, basically this whole piece cancels out and you're just left with that exponent. So we talked about that log property already of that inverse property where they cancel out. So you could do this by hand and you get 8.3. So this is a so this would be an 8.3 earthquake. So when you hear them refer to Richter scale, we're using a log scale there, and it's in reference to the intensity of a 0-level earthquake. So this would be an 8.3, which is quite high. So a little side note here, all of those properties that we've seen earlier, let me go back to them just to remind you that those basic log properties, they apply for any base. So they also apply for the common log as well. So if you have log 10, 10, that's going to be 1. If you have log, again, we just write log, but log 10 of 1, that would be 0. And same thing here. So just remember that these rules apply for any base, including the common logs. And the same rule for domain as well. So this, again, the same rules all apply, doesn't matter what the base is. Another common base that I've mentioned very quickly already is that base E. This is called, it's your natural base. So it's your natural logarithmic function. And what we do is instead of writing log base E, we change it to ln. So think about it as natural log, right? Kind of like backwards, ln and l, natural log. So this is your natural log function. We use it very, very frequently. So we kind of give it its own special name here because we do use it so often. It has many, many applications. The idea of domain still works the same way though. You need to make sure that this is greater than 0. So I take 3 minus x, I set it greater than 0 and I solve. This is just a linear problem, so I'm going to solve by subtracting 3 to both sides. I do have to divide by -1. Remember that when you divide with an inequality sign by a negative, you have to flip that sign. So we have x is less than 3 here. So for our domain, all x such that x is less than 3, or in interval notation from -infinity up to +3 here. Now for this one, this is our function. So that square is on the x minus 3 here. It's not the entire log squared or anything. So I'm looking at x minus 3 squared has to be greater than 0. All right, so in this case here, it's a little bit more complicated. I know you probably can't see it here, but this is not a linear, right? This is going to be a polynomial. So one thing you can do here is remember that this is x minus 3 times x minus 3, and I need this to be greater than 0 here. So think back to how we did polynomial inequalities. What we did is we solved, let's do it in a different color, where it was equal to 0. So in each case, I get x equals 3. And remember that created a boundary point for us. So let me see. Do 1, 2, 3, 4. So we created that boundary point, and then we were able to test and see what our issues were here. So I have to pick a test value in each area, and this goes back to chapter 3. So if you don't remember how to solve inequalities with polynomials or rationals using boundary points, then make sure to go back and review that. So here I'm going to choose 1 for a test point. So if I plug in 1, I would have, let's see, 1 minus 3 squared. Is that greater than 0? 1 minus 3 is negative 2 squared, which is 4. So yes, this is positive. So this is a good area. If I plug in 4, 4 minus 3 squared is 1 squared, which is 1, which is also positive. So this is good. I want positive, right? And hopefully this makes sense. If you square something, it's always going to be positive. The only exception would be if the answer was 0. So there actually is one value to exclude here. Remember, I want to be strictly greater than 0. So that boundary point does not count. If I plug in 3, my boundary point, I would get 0 squared, which is not greater than 0. It's equal to it. So my domain here is all x as long as x is not equal to 3. I have to use parentheses here. I cannot include my boundary point because it's not strictly greater. Or I can do negative infinity to 3 and then 3 to infinity. So go back and review, think about how do we solve inequalities. For the linear ones, they're pretty straightforward, but you do have to be careful. If you divide by negative, you have to flip your inequality sign. If you have a polynomial or a rational, then you're thinking about those boundary points and you're testing in between the boundary points. And that will help you figure out the positive areas that you're looking for. So here, because everything is being squared, almost everything is positive, but we do have that issue of the boundary point. You do need strictly greater than 0 for your domain. So I do have to make sure I exclude 3 here from my domain. And let's do one example for an application for now with natural log as well. When the outside air temperature is anywhere between 72 and 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. And the bar graph shows the temperature increase throughout the hour. So this is your temperature increase. So within 10 minutes, the temperature in the car goes up 19 degrees, and then 29 degrees, 34, and so on, where at the end of the hour, the temperature in the car has gone up 43 degrees. So if it's 80 degrees out, at the end of the hour, the inside of that car is over 120 degrees. This is why you always see on the news warnings and reminders in cases where we don't leave animals, we don't leave children in our cars while we run into the store, because even within 10 minutes, that temperature can get very, very high. Particularly if it's already 90 degrees out. Within 10 minutes, that car is going to be 110 degrees. So again, it's always a warning that we tend to see around here in the summertime, reminding us never to leave, children, particularly in animals and vehicles that are not running, because it gets very, very hot very quickly. This is actually modeled by a log function, the natural log function. So in this case, f of x is going to be degrees in Fahrenheit after x minutes. And it's based on the temperature increase again. So let's use the function to find the temperature increase to the nearest degree after 50 minutes. And then we'll compare it to the actual data. So I'm looking at f of 50 here. And I'm going to go ahead and plug that in. So I have 13.4. Again, this would be multiplication. So times the natural log of 50 minus 11.6. Now, when I write it like this, natural log of 50, that 50 is with the natural log. Sometimes out of personal preference, I tend to actually like to write my number in parentheses there. It's just a personal preference just to kind of remind me that 50 is with the natural log. So we do the multiplication first here. And you want to use your calculator, right? Because we're multiplying these two values. Think about order of operations. Now, in your calculator, you should have a natural log key. It's going to be right here. It's the ln. So I'm going to type in ln of 50 first, where it's multiplication doesn't matter which one I type in first. And I get, again, this really long expansion. So I'm going to use all those decimal places and multiply that by my 13.4. and I get 52.42110827 minus 11.6. When I subtract the 11.6, I get 40. Oops, sorry, I meant to only do it one time. Let's do that again. Natural log of 50 times 13.4 minus 11.6. So 40.82110827. Now this asks us to the nearest degree, so that would be the nearest one or nearest whole. So it's about 41 degrees. And again, this would bump up because of the 8. So the change in temperature after 50 minutes is about 41 degrees Fahrenheit based on our model. How well does this function model the actual increase shown? Well, it's actually very, very good, right? At 50, it was 41 minutes exactly. Our model here also gives exactly 41 minutes. So this is perfect, right on the nose here for that model. Can't ask for anything better, I guess, right? So that looks good. So it models the data extremely well in this case, that we can get that close to the value to the actual real number.